Good morning, students. My name is CH.S.V.PRASAD and I am working as senior lecturer in electrical department at Government Polytechnic, Yadgirigutta. Today we are handling the subject AC motor. In this subject, we are continuing the chapter 4, that is characteristics of three-phase induction motor. In the last class, we have explained about no load and blocked rotor test, how we will conduct the test on no load and blocked rotor test, what we can calculate from these, and how we can draw the parameters, and how we can calculate the efficiency. So that is performance curves of induction motor. So how we can draw the performance curve by using these no load and blocked rotor test, and how we can draw the circle diagram. This has we have discussed in the last class. Today we will find out all the required values of induction motor from circle diagram, and we will solve problems on three-phase induction motor using circle diagram. So how we can draw the circuit diagram? We can draw the circle diagram on graph sheet where x-axis and y-axis we will take like this. On y-axis we will denote the voltage, and first we will take the no load current and no load power factor. We have to take a current scale, suitable current scale, and draw a no load current, that is I naught, that is O A, at an angle of pi naught. Then we have to calculate the short circuit current under normal voltage, that is ISN. With the same current scale, we have to draw a vector OB. This is ISN at an angle of pi s. So, so these two, I naught and pi naught, we can calculate, find out the data details from no load test, and ISN, that is OB, and pi s we can get from short circuit test. So from these two, we will draw OA and OB. OA at an angle of pi naught, OB at an angle of pi s. Then join AB. AB we have to join. Next we have to bisect the line AB and bisect the line AB and extend the bisect line AB until it cuts the AD line at point C. Now we will take C as center and CA as radius, and we will draw a semicircle which touches the point A and D. The points A and B must be in the semicircle. So what we have to do? We will join the AB. Next we will bisect the line AB and extend it so that it cuts the line AD at point C. Take C as center and radius as AC and draw a semicircle which touches the point B like this. So A, B, D is the our required semicircle. You understood this one? How we have to draw? This have we have explained in the last class. So after drawing the semicircle A, B, D, we have to draw a vertical line from B, like this vertical line, and from A also we will draw a vertical line. A cuts the x-axis at H, and and this B line cuts the x-axis at E and AD at F, and we will mark the point G so that AG shows the rotor copper stator copper losses and GF shows the rotor copper losses. This is the stator copper losses and rotor copper losses. If both are same from B to F, B to F shows the B to F shows the copper losses of both stator and rotor. If both are equal, then we have to mark G as center point of BF. For BF, we have to mark the center point as G. If both the rotor copper losses and stator copper losses are equal, both are equal. This BG shows the rotor copper losses and GF shows the stator copper losses. So BG is the rotor copper losses and GF is the uh, stator copper losses. This is the rotor copper losses and stator copper losses. So first I will explain how to draw a circle diagram. So how to draw a circle diagram? The circle diagram of a induction motor can be drawn can be drawn by the data obtained from no load test and blocked rotor test. So for this one, what we have to do? First we have to step one is first we have to calculate I naught and pi naught. I naught and pi naught. I naught and pi naught, and can be found from the no load test. Found can be no load test by choosing proper current scale. I naught can be drawn as OA. OA lags behind the voltage V, which is shown on y-axis OY by an angle pi naught, as shown in figure, with applied voltage as vertical reference axis. So this is the first step, drawing the OA. Next step is from blocked rotor test, IS is known. Convert this IS to normal voltage level, that is ISN. So ISN is equal to IS into V1 by Vs. So what is ISN? ISN is the short circuit current corresponding to normal voltage. So first we have to calculate from block rotor test ISN, that is OB. OB. ISN. ISN we have to calculate. That is the short circuit current corresponding to normal voltage. So next we have to calculate cos pi. So cos pi S is equal Ws by Vs by Is. So with the same current scale, what we taken for drawing the OA, where OA is equal to no load current I naught. So for that one, which scale you taken the same current with the same current scale, the vector OB represents ISN at an angle of pi s. OB at an angle of pi s with the vertical axis. The vector OB, the vector AB represents rotor current I2 dash as referred to stator. So now the 2 points A and B lies on the required circle. For finding the center of the circle, draw a. First we have to join the line AB. AB. So to find the center of the circle, draw a perpendicular bisector from the line AB. This will cut the horizontal line AD drawn from A at C with C as center and CA as radius. Draw a semicircle APD like this. ABD. Draw also a horizontal line OX parallel to the line AD. So we have to draw a parallel line AD. So it forms a semicircle ABD. Now draw perpendicular lines from points A and B on horizontal line as that means from point A and point B we have to draw a vertical lines towards the horizontal line OX. So that is BE, B and AH, B and AH. So this B cuts the AD line at point F so that AH is equal to FE. Also, applied voltage is shown vertical. So all vertical distance represents the activity or energy component of the current, that is AH. That is AH is equal to I naught cos pi naught is the normal input. Thus the length AL can be equated to that no load power, that is W naught, which supplies core losses, friction and windage losses, and small amount of stator copper losses. So after drawing this one, we have to calculate the power scale also. So this is the drawing of circle diagram. This is the drawing of circle. Note down this. Draw the circle diagram. So after drawing this, you can see here it shows all the parameters. That is the how we have to draw maximum output, maximum torque, and rotor. This is B is the rotor copper losses. This is EF is the stator copper losses, and FG is the fixed losses. So OA at an angle of pi naught, OB at an angle of pi SE, and we have to. This is the complete circuit diagram, so that we can find out the required values. The circuit diagram is useful. So how you can draw the further? So to find the, so we have drawn up to here circle diagram. After this, this is circle diagram is over. Next, why we have to, after drawing this, we have to first calculate the power scale. The distance h we have to measure in centimeters. That is W naught, and power scale is equal to 1 centimeter is equal to W naught by AL in centimeters. So uh, that will gives the power scale. So the vertical distance BG, the vertical distance BG represents the input power under blocked rotor conditions. In that, where B shows the rotor copper losses, EF shows the stator copper losses, and FG shows the fixed losses. Now to draw the torque line, this is what is the torque line? This is the line which represents the, this is AE. To draw AE, which represent AE is called the torque line. This is the torque line. So this is torque line, the line which separate the stator copper losses and rotor copper losses. When rotor is blocked, then all the power supplied to the motor is wasted as core losses and copper losses in stator and rotor winding. The power input is proportional to power input is proportional to BG. BG. Out of this BF, out of this BF, uh, sorry, out of which FG and JK or AQ represents fixed loss. FG represents the fixed losses, that is stator core losses and friction and windage losses. FG represents the fixed losses. FG, that is stator core losses and friction and windage losses. The remaining losses B into FB to FBF is proportional to the sum of stator copper losses and rotor copper losses. So to find the point E, so that BE by EF is equal to rotor copper losses by stator copper losses. The line AE known as torque or rotor input line. Rotor input line. So we have to calculate rotor copper losses. So that we have to divide BE by EF is equal to rotor copper losses by stator copper losses. We have to point the fork E and join the point AE. The line AE represents torque line. Torque line. So represents the torque line. So to draw the suppose if you require the maximum torque, maximum output and input of induction motor. So what we have to do it to calculate the maximum torque. This is maximum torque. RS. RS. So what we have to draw first, what we have to do to find out the maximum torque, if the line drawn, so what we have to draw a line parallel to torque line. What is a torque line? AE. We have to draw a parallel line parallel to AE and tangent to semicircle, that is here. This is the parallel line to AE. This is then the vertical distance RS, then the vertical distance RF, that is the tangent line and the torque line. Tangent line is this one, torque line is AE. That represents the maximum torque. The maximum torque is also known as starting or pull out torque. Next, maximum output. If a line is drawn parallel to the output line AB, for AB, if you draw a line parallel to line AB and tangent to semicircle, then the vertical intercept, that is HI. H into this is parallel line, this one parallel to AB, HI, between the tangent line and output line AB represents maximum output. So to get maximum output, to get the maximum output, it occurs at the highest point of the circle, that is V. This is the point V. At point V, where the tangent to the circle is horizontal, it is proportional to VW. VW. It is proportional to VW, as so the point VW represents the maximum input for the induction motor. So from this we can calculate all values. So we can calculate from this, we can calculate rotor copper losses, stator copper losses, maximum output, maximum torque, and maximum input. So fixed losses, everything we can calculate it from this circle diagram. So we can find out various components. So from this circle diagram for the required induction motor, all vertical distance represents the energy components of the currents. Here the vertical distance AQ is equal to I naught cos pi naught, represents the no load input, which consists core loss, mechanical loss and small copper losses. So the vertical distance AQ represents no load input, which consists core loss, mechanical loss and small stator copper losses. full load point or operating point. Draw a vertical line BL which represents the full load output of the motor. Draw a vertical line BL which represents the full load output of the motor. The power scale is obtained after measuring the short circuit power WSN for normal voltage. Since WSN is equal to WSC into V1 by VSC whole square, and where WSN is equal to root 3 V1 ISN and cos pi SC. So this power is equal to the length of the line, that is BG. So you measure the length BG in centimeters. From point L, draw a line parallel to the output line AB, and it cuts the circle at points U and P. Since the normal operating slip is small, then the point P will be the operating point. So from the length of BG, we can calculate the power scale and also find out the length of full load output. Therefore, to get the power scale is WSCN by BG, that is watts per centimeter. Here, the length of the motor full load output is equal to output in watts by power scale. Then it will give the length how much we have to extend, so that to add this losses. So full load current and power factor join OP, which represents the full load current of the induction motor. Therefore, the angle VOP gives the power factor angle, that is pi 1, and it is called power factor at which the motor is operating. So, when referred to full load conditions, motor input, output, and efficiency. So what we have to draw a vertical line from point P to x-axis. That is, from point P we have to draw a vertical line. So this vertical line P cuts that point K. Then noted that points as M, N and J. So if you draw a vertical line, so that is PK, that cuts at 4 points, that is 3 points M, N, J on the vertical axis. When referred to full load condition, the motor input, output, and efficiency, draw a vertical line from point P to x-axis, and it cuts at point K. Then note the point MNJ as the vertical lines here. From P we draw a vertical line PK. it cuts A at a point M, N, J. M is the, so it cuts the M is the point where it cuts the output line. N is the point of interaction which is cutting the torque line, and J is the line which cuts the output uh, horizontal line. So likewise P, K, it cuts M, N, J output line at M, torque line at N, and horizontal line at J. So JK represents again fixed losses. JK represents the fixed losses. So this is the P is the point. So what we have done, we have to find out the full load current. So what we done, we have extended the BL, and we have drawn this parallel to the output line AB, and this cuts the circle at point P. So from this point P, you draw a vertical line, that is PK, which cuts the x-axis on K, PK, and while it passing, it cuts the output line at M, and torque line at N, and horizontal line at J. So JK is equal to FG, that is fixed losses, and MN represents the rotor copper losses, and NJ represents the stator copper losses. So the point V10P represents the angle, that is pi, pi 1. So this is the full load condition. At what is the required load, the OP represents the current, required full load current, and required full load angle, and cos of this cos pi 1 power factor angle, and Mn represents rotor copper losses, and Nj represents stator copper losses. So and Jk represents fixed losses, that is Fg. So from this circle diagram, the vertical distance Pm gives the output, and the vertical distance Pk gives the input of the motor. Here the distance Gk represents fixed losses, as I told. Mn represents rotor copper losses, and Nj gives the stator copper losses. So from this we can calculate, note down this, we have to calculate like this, note down. So this circle diagram is important, he will give for a big question. So now we can find out efficiency, that is output by input into 100. So that is called PM by PK. So directly we can measure PM in centimeters and PK in centimeters into 100. That will gives the efficiency of the motor. So by using this circle diagram, we can calculate efficiency, rotor copper losses, stator copper losses, pixel losses, everything whatever we have, everything we can calculate. So next, slip. So slip S is equal to Mn by Pn. What is Mn? Mn is the rotor copper losses, and Pn is the rotor input. So slip S is equal to Mn by you directly you take scale and measure Pn value and substitute here Mn value and divided by Pn value. Just take scale and measure in centimeters. Mn and Pn. So next one is full load rotor speed ns. Nr is equal to ns into 1 minus yes. Here we got the slip and ns we have to calculate, that is 120 f by p. Note down these formulas. These are important. After doing the circle diagram, drawing the circle diagram, we can calculate the values by using these parameters. Note down it. So efficiency OP, that is efficiency is equal to PM by PK, and slip is equal to Mn by Pn into 100. Next, rotor speed n is equal to ns into 1 minus s. Note down this. Slip is equal to Mn by Pn into 100. Efficiency is equal to Pm by Pk into 100. And rotor speed is normal. So that is equal to ns into 1 minus s. 1 minus s. So torque line. So what we can understand from this torque line, under short circuit or blocked rotor conditions at rated voltage, the power loss is Bg. So torque line, under short circuit or blocked rotor conditions at rated voltage, the power input is Bg. What is Bg? Bg is the rotor block input power. Bg is the power input under short circuit or blocked rotor condition at rated voltage. This shows the core losses and copper losses. So that is the length Fg is equal to Aq, that is equal to fixed losses or core losses. So that is Fg. Measure Fg, that gives the core losses. The core losses of rotor is negligibly increased under blocked rotor condition. So the torque line, hence the length Bf represents sum of stator and rotor losses. The length Bf represents the losses, represents the sum of rotor and stator and represents stator and rotor losses. So next the line AE, which separates the stator and rotor losses, is known as torque line. A is called torque line. So BF gives the sum of stator copper losses and rotor copper losses. AE represents the stator and rotor losses also, but this is known as torque line. A is torque line, BF represents stator copper losses and rotor copper losses. The line AE represents torque line. The torque is proportional to power input to rotor. The rotor copper losses at the rotor copper losses at at standstill are B into E. So BE gives the rotor copper losses at a standstill. So starting torque is equal to BE. So the torque is proportional to the power input to the rotor. So rotor copper losses at standstill is BE. So the BE represents a starting torque. Now separation of rotor copper losses and stator copper losses and short circuit condition. So this can be found. We have to mark the point E, that is BF represents the total stator copper losses and rotor copper losses. In between these two, we have to mark a point E, that is BE by EF is equal to rotor copper losses by stator copper losses, that is I2 square R2 by I1 square into R1. So that is equal to I2 by I1 is equal to I2 by I1, that is R2 by R1 into I2 by I1 whole square, where I2 by N1 and N1 by N2 shows stator to rotor turns ratio. Separation of stator rotor copper losses and stator copper losses under short circuit condition at point E. In case of squirrel cage rotor, the rotor resistance R1 is determined and EF is made equal to stator losses. The input power is approximately equal to copper losses under locked rotor condition, where iron losses are small and neglected. So stator copper losses is equal to 3 ISC square R1. R1 is equal to stator loss resistance per phase, and ISC is equal to short circuit current per phase. So to find the maximum output, draw a line parallel to the output line and the line AB, which represents a tangent to the semicircle. This tangent is in contact with the semicircle at point H. The actual point of contact H is obtained for drawing a vertical perpendicular to the tangent drawn from the circle. So hence HI represents maximum output. So to find maximum torque line, it is also called as starting or full load torque. Draw a line parallel to torque line AE, which is tangent to the semicircle. The actual point of contact R is obtained by drawing a perpendicular to the tangent drawn from the center C. Hence, RS represents maximum output. Next, find out maximum Slip at maximum torque. The slip at maximum torque is equal to Ts by Rs. So to find out maximum input, it is the highest point of the semicircle which is obtained by the tangent to the circle and horizontal to the line AD and OG. The actual point of contact on the semicircle is V, and draw a vertical line from point V which meets the horizontal line OG at W. So VW represents maximum input. So circle diagram, we can calculate OP is equal to full load current, slip is equal to Mn by Pn, that is rotor copper losses by rotor input. Full load power factor angle phi is equal to angle between V1 OP or Pk by OP. Efficiency is equal to Pm by Pk. So maximum output is equal to Hi, maximum torque is equal to Rs, and full load torque is equal to Pn. Starting torque is equal, just you have to measure this Be and convert with the power scale, and slip is equal Ts by Rs. Ts by Rs. So these things we can calculate, all these values we can calculate from circle diagram. Circle diagram. You practice this one. If you have any doubt, ask me in the next class. Thank you.